Hello and welcome student for today's lecture. So let us start our discussion. So this is course number MA425 Topology. Okay, and this is lecture number 3. Okay, now recall in our last lecture we have learned about base of topology and the topology generated by a given base, right? And what was the equivalent form? That given a collection which satisfies some condition, okay, which is called a base. How do we generate the topology? So the topologies are nothing but collection of all union of the elements of that given base, right? So what does that mean? That means the open sets are nothing but the union of the basis elements, right? So basis elements are also open sets. And conversely also you prove that given a topology also how do check a sub collection is a base or not, that also we check. Okay, now today we will do some more properties of base and we will try to compare two topologies from two given base. Okay, so it is easy to compare bases. Okay, so how do we do it? So for that let us do our theorem. So let us discuss with theorem. So suppose we have two topologies on a set. Okay, so let X be a set and some B and some B1. So this is two bases. Okay, they generate two topologies, say tau and tau1, so respectively. So what does that mean? I mean that B generates tau and B1 generates tau1. Okay, so in this case TAVE means the following are equivalent. So what does that mean? That means that I will discuss two conditions. So one is equivalent to other. So if and only the other condition. So what is the first condition? First condition tells you that this my tau1 is finer than tau, and this is equivalent to saying that for each element of X and each basis element of that B which contains X. So what does that mean? B containing X, there exists, if this is given, then what you will get? There exists a basis element B1 which is inside of basis B1 of tau1 with this condition. What is the condition? Such that that B1 contains X, and not only that it is inside the original the base element B of capital B. Okay, so what does that mean? Whenever you have a point and a basis element of first topology, you have another basis element of second topology which contains the points and is also inside the basis element. Okay, so these two are equivalent. So what does that mean? That means to prove something is finer than something, it is enough to find out this condition on basis element. Okay, Now this kind of condition obviously requires a proof, so I will prove this thing properly. So proof. So there are two conditions. So let us first prove that 1 implies 2. So what does that mean? That means I assume that. So assume that tau 1 is finer than tau. What does that mean? That is, this means that tau is a subset of tau 1. Okay, so this may be equal or maybe proper subset. Okay, clear. So so this is the assumption. So now I have to prove that under this assumption the condition 2 is true. So what was the condition true? So for that, let you find out an element. So x belongs to x, and we have a B element which is element of the basis B, such that x is element of B. Okay, this is given to you. And now as tau is a subset of tau 1, so what do we have? We have here that B is an element of tau 1 also, right? Because B is an element of tau. B is a basis element, and every basis element is also open, right? So what does that mean? That means every basis element is open, means this is also inside that topology tau. Okay. Okay, so so this is I mean this condition is true, right? Now to show what I need to show that okay, so now I need to show that this basis element is a element of the so there exists a element of the basis of B1. So this condition basis B1 which actually contains the set point x and also inside that the given basis element, right? Now this is obvious from the definition of tau 1. So what is tau 1 tells you? Tau 1 tells you that tau 1 is a topology generated by BC. Okay. Now by again I can write down again tau 1 is the topology generated by this B1. Okay, so what does that mean? That means elements of tau 1s are, I mean, see, there are two ways. You can say that elements of tau 1s are unions of elements of B, or what was the definition of this basis? So it contains all the elements which are open sets, such that whenever you have a point on that open sets, you have an element of B1 that contains the points and inside the set, right? So as again this, so what we have, so see B is element, B is open set, right? And open set in tau 1, under tau 1, this topology. So by as B1 is a basis, so there exists obviously B1 belongs to this capital B1 which is basis, such that this is by definition of definition of the basis of tau 1, such that your x is element of B1 which is also inside B, right? This is just proper definition. Okay, and this proves actually so which is actually condition. So this is actually condition 2, right? Okay, done. Now I need to prove the converse part. So 2 implies 1. Okay, 2 implies 1 means what? So it is given that for every element of x and every basis element B containing element of basis B, say small b, that contains that element, you always have another basis element of B1 which contains the points and which is also inside that given basis element, right? This is given to you. Now you need to prove that tau 1 is finer than tau 2. What does that mean? That means tau 1 is bigger actually, right, as a collections. So every so what need to find? So we need to show, what you need to show? We need to show that tau is a subset of tau 1, right? This is need to show. So to show this thing, what you need? So I need to show that every open set here is also open set here. Okay. So start with that. Let U belongs to tau. I chose a open set in this. So I need to show that U is element of tau 1. And so let U belong to this, and you choose an element of U. Okay. Okay. Now we know that. So this tau is actually generated by this basis element. Okay. So this is my symbol. That the symbol tells you that tau is a topology generated by this basis B. So if tau generated by B and U is open set in tau, what does that mean? That means that there exists you have some element which is elements of the basis B, such that your X is element of B which is inside U, right? This is by definition. Okay, but the moment you have an element which contains X and B, and then condition 2, now from condition 2 we have what we have? We have a basis element B1 of B1 such that what? Such that my X is element of B. Such that my X is a element of B1, and which is also inside B, but B is inside U, right? So what does that mean? That means I have a basis element B1 of the topology tau 1 which is inside U, right? And this implies that U is element of tau 1, and thus tau 1 is a subset of tau 1, right? Because every open set of tau is also open set in tau 1, and hence tau 1 is finite then. So thus tau 1 is finer than tau. Clear? So this is a simple proof that tells you that whenever you want to compare two topologies, then you need to check. It is enough to check on basis. Okay, because some times bases are easy to understand, easy to also formulate. So you check whether for a point and a basis element containing that, you always have another basis element inside that or not, and vice versa. Now to prove that two topologies are equivalent or same, okay, so what you need to prove? Or two bases generate the same topology. What you need to prove? You need to prove that this condition 2 is true for both the topology, both the basis elements. So what does that mean? For every open set in B, you have open set. Every basis element in B, you have a basis element to B dash that inside that, and vice versa, conversely. Okay, then you can, maybe I will give an example, then it will be clear. Okay, so let me give an example, proper example to elaborate this theorem. Okay, so example. Okay, so so for example, so let me discuss R2, which is R cross R. Okay. Okay, so I did not, I see, there is something called product topology. I am not defining that thing. I am just, this is as my plane. R2 is my plane, and here I want to define a topology on that plane. And so first of all, it is easy to define the basis instead of the open sets. So how do I define? So let me define that my B1 and B2. Okay. So what is my B1? B1 is this interior of any open any these circles. This is my B1 interior. So you understand the mean without boundary. Okay, this is my B1 and that collection, and B2 contains a collection of interior of say rectangular region. Okay, so let me write down that thing. So B1 is collection of this how do I write? Maybe I can write down that circle, solution of circle without boundary, circles. Okay, similarly B2 is collection of rectangles without boundaries. Okay, so obviously you can easily check that both B1 and B2 actually forms a basis. Okay, so this is obvious. Why? Because first of all, obviously this the B1 is a basis of R2. Why? Because see, the condition, both the condition B1 covers R2, right? So if you choose any element, any point on plane, you can always find out a circle that contains the thing, right? And number two, also you remember the second point, that if a point is inside two elements B1 intersection B2, and then there exists some B3, and thus that is element of B3, which is also subset of B1, B2, and that is obvious. You can easily see by pictorially. Suppose you have two elements, okay, two circular edges, okay, and you have a point X, and this is your B1 and B2. Then you can find out another circular element that contains a point, and this is your B3, and you see that this can satisfy this condition, right? So you can always find out this property true, and B1 is a basis of R2 for some topology. Okay, similarly you can check that this B2 is also the script B2 is also topology, basis for a topology is also a basis for some topology. Okay, on R2. Why? Same thing. First off, obviously B2 also covers, right? B2 covers R2, and obviously second condition also true. Pictorially, let me draw. So whenever you have suppose a points which is intersection of two elements, basis element, so B1 and B2, and you can always find out the small rectangles that containing the points, and is also subset of the intersection of B1 and B2, right? So this is this also tells you that B1 B2 it's capital script B2 is also a topology, basis for some topology, right? Now question is that the moment I have basis elements, so I can generate the topology, right? Like you take the union of all such things in both the cases. So let me write down so what I'm writing, B1 B2, right? Yeah, so let me write down my tau 1, which is topology is generated by B1, and tau 2 topology generated by B2. Okay, so suppose this is my symbol. And the question is that whether you can compare these topologies or not. Okay, so we just prove that to compare, like if you say something is finer than something or not, it is enough to check on the basis element, right? So can we do it or not here? Now pictorially I will give you a simple solution, but obviously mathematically also you can prove the same thing. So what I need to prove? So given to prove, for example, let me first check that tau 1 is finer than tau 2. So tau 1 is finer than tau 2 means what? So every basis inside every basis element of circular region, you have a basis element of rectangular region. That is obvious, right? So given a point and you have a circular region, suppose okay, so you just assume that this is a circle, though it doesn't look like exact circle, just assume that, okay, interior of the circle, okay, you can always find out a basis element from tau 2. How? This is the basis element, okay. And conversely, if you start with the basis a point and the basis element of B2, you can always find out a basis element which contains that point, same point, and this is nothing but this circular region, right? Okay, so what does that mean? That means both tau 1 is finer than, so this first one tells you that every tau 1 is inside tau 2, and second one tells you that tau 2 is inside tau 1, and hence they are equal, right? Tau 1 equal to tau 2. So what does that mean? That means these two bases generate the same topology on R2, right? So this is clear that even if you have a basis which is a different representation, but the topologies they generate, they are same. Okay. Yeah, so now I will give some example where you can have a different topology, not the same topology. Okay, so so maybe something is strictly finer than another one. Okay, so now let us discuss some more example. Okay, some more examples. Okay, so now you recall that inside R we already know one topology, which is called Euclidean topology, right? We already discussed Euclidean topology on R. Okay, and what was the basis? So basis are nothing but collection of all open intervals of this form, right? So A and B, A less than B, and A B element of R. These are element of R. Okay, and this is actually there is something called order topology. Maybe if I have time, then I can discuss. Let me discuss now. So what is an order topology? Let me discuss. Then you can see that this is actually forms order topology. So and the topology tau generated by this is called the Euclidean topology or the standard topology. It's also order topology. So let me define here what do you mean by order topology. Then you will understand. Order, I think, yeah, order topology. So one important thing I should say that or rather I think it's called order topology. Okay, so so yeah, so what is an order topology? So suppose if you have a set which is have a some ordering, some ordering is there. So ordering means what? So you can define two elements. Okay, so given two elements A and B belongs to X, so you can say that A less than B, something like that, B less than A, something like that. Okay, and there is something called so then X is called a simple order set. So X is called a simple or simple order set. Okay, there is something called well ordered set. So that means that you know the meaning of well ordering principle, right? Every non-empty subset of natural number has a least element, right? So similar properties would be true here. So and what is that? So well order set. Well ordered set means what? So a set is called a well ordered set if every non-empty subset has a least element, right? So this property we already discussed many times in, I think, last time also, last algebra course, least element. Okay, and so what is the order set? Order set may be well ordered, may not be well ordered, right? So it's just on containing a order, right? So now I am starting with the order set, simple order set. So maybe this is my definition, you can say, of order topology. So let X be a simply order set TID. So I am not saying well ordered, it can be well ordered also, okay. And I'm also assuming that that X has at least two elements. Then I can define by this, okay. Then I will define a basis element. So, and then I will say that this is actually forms the topology forms generated by that is called the order topology, okay. So the collection B of the following set forms a basis. What are the sets? So there are three types of sets. So first type is what? Obviously the natural one, that AB, such that A and B, A less than B, right? So this natural sets. So you collect all such elements, okay. And number two, so for example, this is well ordered set, right? So it may have a least element or may have a large element. So if it has a least element, so let if A naught be the least element of X. So if I am saying if, so if it is not there, then we are not taking this collection, right? If this is a least element of X, then we also take this collection, all A naught and this close A naught, open B, okay. So this is least, so obviously, okay. Similarly, another collection, so if you have a largest element, say B naught be the largest element of X, then what we will choose? Then we will choose of the elements open A and close B naught, okay. So these collection, three collections, they forms a basis, and this is obvious, they forms a basis because obviously this covers the false space, and whenever you have intersection of two elements contains element, you always have an element inside that, okay. So this is trivial fact, you can check homework, okay. So the topology now in case of R, when X equal to R, you see that number 2 and number 3 are empty collection. There is no such element, right? Because inside R there is no least element, neither there is a largest element. So that is only R. That's what the so okay. So let me finish that. The topology generated by B is called the order topology, okay, on X. So order topology on X. Okay, so this example that when x equal to r, the topology with the Euclidean topology is the order topology. The Euclidean topology, is order topology. Okay, clear. So this is an order topology. Okay, so now question is that can you define can we define some defined topology on R? The answer is yes. Now let me define some more topologies and check whether there are relation between these two topologies, like something is finite there something or not. Okay, so let me define another topology, another say basis. So this is B1, and B1 is collection of all such interval of the form which is something called half open, half closed. Okay, so open A, close B, and this, sorry, A, B is A less than B, and this element of R. Okay, clear. Now this is my set, and also you check that this also forms a basis, and this is obvious why it also forms basis, because these collections covers R, and not only that, whenever you have any two such intersections elements, for example, you choose like empirically, let me write down. So suppose this is one element and this is another element, and then you check that. So this is your first element B1, and this is second element B2, and then inside that you will have that B3 that sitting inside. If some point is sitting inside the intersection, then that contains inside B3, right? This is also of the same form. So B3 is also a basis element. Okay, so B1 is also forms a basis for some topology, right? Or maybe okay, so maybe let me write down this by the name BL. Why I am writing L, you will understand. Okay, and the topology generated by this, let me write down tau. Okay, so this is my definition. Tau L is a topology generated by this BL. So what does that mean? That means tau contains all the elements are open sets which are a union of any kind of union of elements from BL. Okay, and then I will write down RL is what? RL is nothing but R with this topology. Okay, this order pair. So the moment I say RL, I mean that the real number with this topology, and this topology is called the lower limit topology. This is very, very important topology. Okay, so the lower limit topology. Obviously, you will understand why I am saying this lower limit later, because when you talk about limit points, other things, sequence, compactness, you will understand more. Okay, so lower limit topology on R. Okay, clear. This is obvious, and then you can obviously okay, there is one more topology, let me define, and then we will try to compare these two topologies. So another topology I can define my basis elements. So okay, so before that, let me define another set. So let me define that K is collection of elements of the form 1 by n, such that n is a natural number. Okay, so I am taking that all reciprocal of the natural numbers, and I am defining my BK, which is what? Which is obviously that the BL, sorry, the original B, the open sets union sets of the form this. So obviously, see, original B means that the equivalent topology. Okay, so all the open intervals are open interval, the open set, right? The open set generated by the open intervals, and then with that I am writing another type of set AB minus K. So what does that mean? That means you choose also those intervals minus these reciprocal points, okay, and AB also element of R. Okay, so what does that mean? That means so open sets are what? So basis elements are basis element of these forms and also of this form, AB minus K. So you are throwing out these reciprocal elements from this. For example, you can choose -1 1 minus K. So what does that mean? It is all the real number from 1 to -1 to +1 without these reciprocals. Okay, this is also basis element here. And then you define the topology tau K, which is a topology generated by this BK. Okay, and then you write down your RK is your real numbers with this topology tau K. Okay, so this is another topology, and obviously now you have a equivalent topology, a lower limit topology, and this topology is called the K topology on R. Okay, so this is called the K topology on R. Okay, now the natural question one can ask that out of these three topologies, are there any relations? And the answer is yes. So what is the answer? So you can write down the theorem that this R is strictly inside both RL and also RK. So what does that mean? That means RL and RK are strictly finer than R. What does that mean? That means you have every open sets of R is inside this, and conversely there are elements inside RL which is not inside R, and same thing here. Okay, and this requires a proof. So so how do you prove that? So to prove, so let me first prove this part that okay, so let me first prove that R is strictly inside RL. Okay, and this is almost obvious because whenever you choose a basic open set, element of basis, right? See, we just proved that in first theorem. What was the theorem? The given a basis and a point inside the basis element, then you will always find another basis element of the other set which contains that, right? So you choose, so let so for example, X belongs to R and AB in open interval belongs to R such that X is element of AB. Okay, now can I find out a basis element of RL which contains X and which is inside this open interval AB? And the answer is yes. And what is that? Then obviously this is this, right? You see that open closed interval X to B. So this is a basis element of RL, and this is element, this contains X also, and this is also inside AB, right? This is obvious. Okay, and so this is obviously, this is inside you just check, this is inside this BL, so this is open sets of RL, right? And that will tells you that R is actually inside RL. Now I need to check that this is strictly finer. So this tells you that RL is finer than R, but I proved, I tells you that this is strictly finer. So what does that mean? That means that conversely you can find out some element which is not inside this thing, right? Now how to find out? For example, you choose, so let something say Y C. So this is you choose a set inside this topology, okay, tau L, okay, and Y is element of this, right? Now can you find out? See, now there is no open set in tau, that usual topology containing y and is a subset of this open set of tau L y to C. Okay, there is nothing. So what does that mean? That means these kind of open sets are not inside R, like under usual topology, right? So that tells you that your this topology tau is strictly finite than tau L. So tau L is strictly finite than tau, right? So this is not the right symbol. I should not say this. I should say rather tau is finite. Tau L is finite than tau, right? Oh, okay. So this is the first proof, and second proof for the second thing for the K topology. Also, this is similarly you can also always prove it. So I mean to say that tau is also strictly finite than tau k. So this is actually I want to say, okay, when I'm saying the strictly finite, so I mean to say that I don't want to say that this symbol, okay. So this topology is tau k is finite than tau, okay. So this is I want to prove, and that is obvious. So because every open set of the form, if it is in tau, it is also inside tau k, right? So this is not the problem. So one part is obvious. So the important thing is that do we have an element of the set here which is not inside this? And the answer is yes. I have given you an example already, right? That -1 + 1 k, right? So this is inside tau k because this is one of the basis open set, right? But you see that there is no such elements of open sets of tau which contains B, which is inside B. Okay, so and you choose a point at 0, so 0 belongs to B, right? But okay, so there is no open sets in tau containing 0 and inside this set -1 to +1 k, okay, because the moment you are removing the point k, it cannot be inside that, right? Obvious. Okay, so this is the proof that these two are actually finite than the usual topology. Now you can ask another question whether the origin topologies are also equivalent or not, and then that you can just check it whether they are comparable or not, right? Like what about this? So you can check homework that for tau L and tau k, can you say anything? Like, can you compare tau L and tau k? Okay, so yeah, so I will finish this chapter to the lecture by defining the last things, and this is another idea is called a subbase, and then I will stop today's lecture. Okay, subbase, or some people call subbasis. Subbase of a topology or subbasis of a topology. So what is that thing? So a collection is called so when I'm saying collection, I mean this is actually subset of the power set of X. Okay, X is given, right? Subset called a subbase for a topology. Okay, for a topology on X, if X, that collection is covers X. So what does that mean? That means that for every element of X there exists an element of X that contains that. Okay. Okay, so collection of so this is the meaning of subbase. So whenever you choose an element of X, you will have an element of X that actually contains that point of X. And then how to generate topology? So from subbase, how to generate topology? So you generate topology like this. So you take union of any kind of union of that B alphas, whatever, any union. And what is B alphas? Each B alphas are actually that final intersection of some kind of final intersection. So I equal to 1 to in alpha of element of this SI is element of that subbase. Okay, so what does that mean? So subbase is a collection where if you take the final intersections, they actually become the base. You understood? That's why you are taking infinite union to become the topology, right? So this is one of the important things. So you choose those collections whose intersection become a base, and those collections are called those collection is called a subbase. And obviously, how do generate the topology? You take the final intersection and then take the union, and they will become the open sets. For example, let me give an example. Obviously, it will be clear if I give examples properly. So that R with the Euclidean topology. Okay, topology. So inside Euclidean topology, you know that you have open sets bases are nothing but open intervals, right? And now you can define something called subbasis. So what is that? So this is my open race. So what does that mean? So let me write down these symbols. So this is of this form. Okay, and this is left open. See, this is infinite in left side, and also you can have right side also. Okay, so collection of all such things are called the open rays. Okay, they are called open rays. Ray means light, right? Open rays. So from left side to A and from B to right side. Okay, any such thing for any AB. Okay, for AB belongs to R. Okay, now you see that these forms a subbase. First of all, this covers the full thing, that there is no doubt about it. And second, I mean, how do you get B? So if you take intersection of this element, they actually becomes nothing but either empty set or these intervals, right? Open intervals, and they actually become basis B, and hence you can define the topology, equivalent topology, by taking final intersection of this with the union of those intersections, right? Clear? So this is one example. Now you can obviously try to find out other examples from other topologies. Okay, so maybe I will stop today's lecture. So and tomorrow we will learn some more interesting topologies. Okay, let me stop.